To understand organic chemistry, you must know the various electronic effects in organic chemistry. Now, the first one is mesomeric or resonance effect, the second one is hyperconjugation, and the third one is inductive effect. To study mesomeric or resonance effect, you must know what is resonance. Now, before studying about resonance, let us see two experiments. In the first experiment, we take two bar magnets, two small bar magnets, and place them in such a way that their opposite poles face each other. Now you slowly bring these magnets closer until their fields just overlap. Now at this point, the magnets will move spontaneously forward and come into contact. Now this is a stable situation because there is no further movement. Now when the magnets move forward, kinetic energy is needed for this process, and this is taken from the potential energy of the system so that the potential energy of the system decreases. So to attain stability, there should be a decrease in potential energy, or potential energy of a stable system is a minimum. Now suppose we are holding the magnets tightly at the point where they start to move spontaneously. Now we can prevent the movement, but we are supplying our own energy to the system, and since this energy is not utilized for motion, it is taken as the potential energy of the system. So the potential energy of the system increases. But still the system is unstable because once you remove your hands, the magnets will move spontaneously forward. So we infer that potential energy of an unstable system is very high. Or we can keep an unstable system as such if the system possesses a very high potential energy. Now coming to the second experiment, you take a solenoid which is a coil of conducting wire. You connect the two ends of the solenoid to the poles of a battery. Then, according to physics, positive electricity starts from positive pole, passes through the coil and reaches the negative pole. But according to a man of chemistry, electrons start from the negative pole, passes through the coil and reach the positive pole. Now whatever be the case, a magnetic field is created along the axis of the coil. So an iron rod kept along the axis will get magnetized. From this experiment, we infer that whenever electron is moving circularly, a magnetic field is created along the axis passing through the center of the circle. The same idea can be extended to a single electron revolving around its own axis. Now there is no such axis, but we suppose that the electron possesses an axis. Then the revolution of this electron around its axis is called the spin of the electron, and the electron can spin in a clockwise manner or an anti-clockwise manner. Suppose the electron axis is spinning in the clockwise direction, and suppose a north pole is created at the top and a south pole at the bottom. Now another electron spinning in anti-clockwise manner will create a south pole at the top and a north pole at the bottom. Now these two electrons can attract each other because of the opposite poles created on the same side. So north attracting south and south attracting north. So this attraction results in a decrease in potential energy and increase in stability. So electrons with opposite spins can attract to some extent, but we should remember that the predominant force between electrons is that of repulsion. But again, this slight attraction and consequent stability is enough to accommodate this pair of electrons into a single orbital. A third electron trying to enter this orbital will be repelled by any one of the electrons because of their similar magnetic dipoles. This may be the reason behind Pauli's exclusion principle, which states that more than two electrons cannot be accommodated in the same orbital. Now, another consequence of this observation is that whenever there is a chance for movement of electrons in a molecule, the molecule will do so such that electrons move in pairs. Now coming to the example for resonance. The most familiar example for resonance is that of benzene molecule. Now benzene can be represented by two different structures. Again, for a given molecule only one structure is possible, but for benzene here we can draw two similar structures. They differ only in the position of their pi bonds. Now you take your photo and you will get your photograph. You again take your photo, you will get the same photograph. But here benzene has two photographs or two different structures. So that is impossible. And resonance theory gives an explanation to this phenomenon. According to resonance, the pi bonds in benzene are always in motion. Now consider the pi bond between position 196, carbon 196. It will be moving in the direction as shown by the curved arrow to a position between 1 and 2. Now the curved arrow starts from the pi bond, from the middle of the pi bond, and ends at the middle of the carbon 1 to carbon 2 bonds. Now simultaneously this 2,3 bond will be shifting in this direction and 4,5 bond will be shifting in this direction. Now all these bond movements are simultaneous, because when this bond shifts in this direction, the valency of carbon 2 becomes 1 plus 1, 2, 3, 4, and there is a CH bond. So total valency becomes 5. So carbon cannot have a valency of 5 because its valency shall contain only 4 orbitals. So to maintain the valency to 4, this bond will be shifting in this direction. And then again the valency of carbon 4 becomes 5 because 1, 2, 3, 4 and a CH bond giving a valency 5. So that cannot be accepted, and so simultaneously this bond will be shifting in this direction. And when this bond shifts in direction, the valency of carbon decreases to 3, and when this bond comes here, the valency of carbon 6 becomes 4. So all these bond movements or electron pair movements are simultaneous, and we get structure 2. In structure 2 also such movements occur, so that we can get back structure 1. So these pi bonds or pi electron pairs are continuously moving along the hexagonal ring structure of benzene. Now let us see one analogy for resonance. Unicorn is a historic animal, that is a non-living animal found only in history. Now its speciality is that it has a horn on its forehead, and speciality is denoted by the term character. Character doesn't mean its behavior but its speciality. And the main character of another historic animal, that is non-living animal, is dragon, and its characteristic is a tough skin. So main character of unicorn is a horn on its forehead, and main character of dragon is a tough skin. Now these two characters are found in a living animal called a rhinoceros. So rhinoceros has got both a horn on its forehead and a tough skin. So we can consider rhinoceros as a hybrid variety of these non-living animals, that is unicorn and dragon. Now suppose structure 1 is unicorn and structure 2 is dragon. We can consider the real benzene molecule as the hybrid of these two structures. So structure 1 and 2 are unreal structures like unicorn and dragon, and the resonance hybrid given by this structure is the real structure of benzene. Then let us see how this resonance hybrid structure is obtained. Now since 1 and 2 are similar, they have same potential energy or same stability, so that their contribution of character will be equal. Suppose structure 1 contributes 50% character, then structure 2 also contribute 50% character. Now in structure 1 the 1,6 bond has 1 pi bond character. In structure 2 the 1,6 bond has 0% pi bond character. Now combining these two characters, that is 1 pi bond into 50% and 0 pi bond into 50%, summing these two we get 1 pi bond into 50%, that is 50 by 100 equal to 1 by 2. So the 1,6 bond in the real structure or resonance hybrid will have half pi bond character. We cannot represent by valence bond theory a half bond, so we put dotted lines between carbon 1 and 6 indicating that it is a half bond. Similarly, you consider all other bonds, carbon-carbon bonds, all will have 50% or half pi bond character. So this will be the approximate structure of the real benzene molecule or resonance hybrid. Now this structure is not accepted by valence bond theory. Why? Because when we take any carbon, its valency becomes 5, because there is a CH bond here on carbon 1, and these two valencies and these two valencies all add to 5. So this cannot be accepted by valence bond theory. Anyway, this approximately represents the structure of resonance hybrids. Now again, the pi electron pairs are moving continuously over the entire ring system from carbon 1 to 2 to 3 to 4 to 5 to 6 and then again to 1, so that the length of movement of electron increases. So electron pair moves to a longer distance in the real structure, that is resonance hybrid. Initially the pair was restricted to a pair of carbon atoms in the canonical structures or unreal structures, but in real structure the electron pair is moving over the entire carbon structure, carbon skeletal structure, so that all the electron pairs are embracing all the carbon atoms. So all the carbon atoms have access over the entire pi electron system. So the movement of pi electrons occur along the ring system or all the carbon atoms. So the length of movement of electron pairs increases, and as the distance moved by electron pair increases, more kinetic energy is needed for this process, and so there is a larger decrease in potential energy in the system. So in the real structure resonance hybrid, since electrons are moving a longer distance, a higher potential energy is needed for this movement. So there is a greater decrease in potential energy and a greater stability attained due to this movement of electrons. So the resonance hybrid is more stable than any one of the canonical structures. Then it is found experimentally. Usually spectroscopic experiments are used to find out the length of bonds and the strength of bonds in a molecule. It is found experimentally that a carbon-carbon double bond as in ethylene is having a length of 1.33 angstrom units, and a carbon-carbon single bond as in ethene is having a length of 1.54 angstrom units. Now in benzene, it is found experimentally that all carbon-carbon bonds are of equal length and equal strength, and is equal to 1.4 angstrom units. So here all bonds have equal length because all bonds have 1.5 bond order. So bond order of all carbon-carbon bonds in the resonance hybrid, the real molecule, is equal to 1.5, and this is in between a 2 carbon-carbon double bond and a 2 carbon-carbon single bond. Now we can alternatively represent the resonance using a circle inside the benzene ring system, indicating there is a circular movement of electron pairs. Now the electron shift in a benzene molecule may be understood in a different way. Suppose the pi electrons between carbon 1 and 6 move entirely into the orbital of carbon 1. That means the pi bond ionizes, the bond breaks, and the orbital over carbon 1 possesses a pair of electrons, and the orbital of carbon 6 and the orbital of carbon 6 possesses a vacant orbital. And carbon 6 possesses a vacant orbital and carbon possesses a filled orbital. Now since the orbital of carbon 6 is taking up both the electrons, it should get a negative charge, and carbon 6 should possess a positive charge. So carbon 1 possessing a pair of electrons and a negative charge, carbon 6 possessing a positive charge and a vacant orbital. Now here a negative carbon will be sp3 hybridized, and the bond angle will be near about 107 because this situation is very similar to an ammonia molecule, and carbon 6 possesses a positive charge, and a positive carbon is sp2 hybridized, so that the bond angle here will be 120 degree. So all the negative carbons will be sp3 hybridized and will be having bond angle near about 107 as in ammonia. Now the situation is a little unstable, and what happens is that the filled orbital of carbon 1 will overlap with the vacant orbital of carbon 2, and the filled orbital of carbon 3 will overlap with the vacant orbital of carbon 4, and the filled orbital of carbon 5 will overlap with the vacant orbital of carbon 6. Now during these overlaps, two things happen. One is the change of hybridization of the negative carbon from sp3 to sp2, and then one electron of the lone pair becomes the property of the vacant orbital here, so that when one electron is lost from this orbital to this vacant orbital, its negative charge is lost and its positive charge is also lost. So we get this structure. So this is a detailed way of understanding the bond shift. Then coming to another term called resonance energy. Now potential energy is equivalent to a chemical term called free energy. So in chemistry, we deal with molecules, and the more suitable term for energy is free energy. And free energy and potential energy are comparable. They are proportional. As potential energy increases, free energy also increases, and as potential energy decreases, free energy also decreases. Now there is a term called resonance energy, which is the difference between the free energies of the resonance hybrid and the most stable canonical structure. So resonance energy equal to free energy of the resonance hybrid minus free energy of the most stable canonical structure. In the case of benzene, the two canonical structures have equal free energy because these structures are similar, represented by F1, and the resonance energy of benzene is given by F2 minus F1, where F2 is the free energy of the resonance hybrid. And the resonance energy of benzene is calculated by experiments, and it is found that it is equal to 150, nearly equal to 150 kilojoules per mole. Now this is the resonance energy of benzene, a fairly high value, and usually the resonance energy will have a negative sign indicating that there is a decrease in energy, free energy, during the formation of the resonance hybrids. Greater the resonance energy, higher will be the stability of the molecule, real molecule, that is resonance hybrids. Now you take another example, that is butadiene. Now butadiene contain a double bond between carbon 1 and 2, a single bond between carbon 2 and 3, and a double bond between carbon 3 and 4. Now this double bond is alternate to this double bond. In benzene also we have alternate single and double bonds, a double bond, single bond, double bond, single bond, double bond, and single bond. So such molecules which contain alternate single and double bonds are called conjugated molecules. So butadiene is a conjugated molecule, benzene is a conjugated molecule. Now suppose the electron pair, pi electron pair between 1 and 2 shifts in the direction shown by this curved arrow. So it comes in between 2 and 3. Then during this movement, the share of electron of carbon 1 is lost, and that carbon 1 gets a positive charge. Now when a new bond is formed here, the valency of this carbon increases to 5 because 1 plus 1, 2, 3, 4, and CH bond is there, 5. So to maintain the valency to 4, this pi electron pair shifts like this. This arrow indicates that the pair of electron in this pi bond is moving entirely into the orbital of carbon 4. So we have carbon 4 with a pair of electron, and since the pair of electron is moving, one electron is the share of this carbon gets an additional electron and a negative charge. So this structure is one of the canonical structures of butadiene. Now the bond shift can occur in an opposite direction like this. In this case, carbon 1 gets negative charge and carbon 4 gets a positive charge. Now examine these two structures. They are similar. They differ only in the position of the charges here. Now structure 2 and 3 possess separate charges. Now this situation is just like the situation of two magnets with their opposite poles facing each other at the point of overlap of their fields. So they tend to move forward, and to prevent the movement we are holding the magnets tightly so that we are supplying our energy, and the potential energy of the system is increased. The system is still unstable because once we release our hands, these magnets will move forward. And to keep an unstable system in that state, a high potential energy is needed. Here we have opposite charges. They tend to attract and to keep these charges in their position, a high potential energy is needed. So that potential energy is of structure 2 and 3 will be very high. So they are highly unstable structures. Now, according to resonance theory, an unstable structure contributes little character to the resonance hybrids. So that the percentage of character contributed by 2 and 3, which are similar, will be equal and lesser. Suppose structure 1 contributes 90%, then structure 2 contributes only 5%, and structure 3 contributes only 5%. Now, in the resonance hybrids, all the bonds will have pi bond character. So between 1 and 2, in structure 1 there is a pi bond, but in structure 2 there is no pi bond, in structure 3 there is no pi bond. Between 3 and 4 there is pi bond in structure 1, there is no pi bond in 2 and 3. So when we combine the characters of all these structures, between 1 and 2 and 3 and 4 we have partial double bond character, pi bond character indicated by dotted lines. Now between 2 and 3, structure 2 and 3 possess pi bond, structure 1 does not possess any pi bond. So combining the characters, all the characters of these canonical structures, we have a partial bond between pi bond between carbon 2 and carbon 3. Now the charges of carbon 1 and 4 are neutralized because these two structures contribute equally to the resonance hybrid. So the charges positive and negative with equal percentage will neutralize each other, and here also neutralization occurs. So in the resonance hybrid there will be no charge over carbon 1 and carbon 4. Now coming to the resonance energy of butadiene. Now the most stable canonical structure of butadiene is 1, and the energy difference between, that is free energy difference between structure 1 and the resonance hybrids will be the resonance energy, and it is found to be equal to 14.6 kilojoules per mole. And since 2 and 3 are highly unstable, their contribution of character will be less, and so the structure of butadiene is almost the structure of the most stable canonical structure, and so the resonance energy is low because stability will be low. Thank you.